Okay, so let's go on. 3.2 is called the graph of a function. Okay, so you start off with some function f from r to r, say. So you have some function, you have some function f, okay, and then you know, this is really, it's a rule, right? We think of this thing as a rule, a law associating to each point here, some unique point over here, right? But we represent it, and we know this already, we represent the function, or if you want to be specific, sort of the law of the function, graphically, by saying, by requiring x, y, by requiring, say, x, y to be on the graph, f, if and only if y equals f of x. So we define a graph, we create a graph, we create a graph of f, right, in this way, right, on the, right. So, just to be kind of silly, if I have 2, 3, so this point 2, 3, let's say that this is the graph of some function f. And let's say that 2, 3 is on the graph. What does that tell you? So you should be sort of groaning. What does that tell you about the function? If 2, 3 is on the graph, what does that tell you about the function? Taylor, what does it tell you about the function? 2, 3 is on the graph. It's ready, it's completely, what does it tell you?
The line goes to the point 2, 3.
The graph goes to the point 2, 3, that's true. What does it tell you about the function? Rebecca?
2, 3 is a solution?
2, 3 is a solution? F is just a function. This,
I know that.
this,
You do.
okay,
It's positive, something?
the function is positive.
Maybe too obvious.
It's actually much more obvious than the things that you're saying. Sophie?
That you can plug 2, 3 into the function.
That you can plug 2, 3
So
into the
if
function.
you put in 2, you'll get 3.
Okay, if you put in 2, you get 3. Yes, that's it.
Mm.
Okay, and f of 2 is 3. Okay. So, right, that's what it means to be a point on the graph, right? X, y being on the graph means that the y value is f of the x value. Okay. And it's completely obvious, but for some reason doesn't seem to be completely obvious. Even people in like calculus, calc 1, 2, 3, something is funny. There's some sort of disconnect between the meaning of the graph and the meaning of the graph. Okay. Yeah, strange. Okay. So right, basic examples. Right, if I have something like this, I don't know, if I have that f is the absolute value function, right, then you know what the graph looks like. What does the graph look like? So you tell me. It's like a V, right? Right, all points, right? You take some point here, right, x, and the y value is going to be absolute value of x, right? So it's the same x, right? Right over here, the y value is the same, right? But over here, when I take in x, what's the y value? What's the y value? Yeah, if x is here, and this is the absolute value function. X is a negative number. The y value is. So what is it? negative x, okay, right? So here we don't get x, we get x negative x, right? Here we get x, let me call this things p. So p, and then my move over, we get p negative p, right? Right?
It's backwards.
Right? Because p is a negative number.
Okay.
Because p is a negative number, right?
You say so.
P is negative, negative p is positive. Right? Okay. Again, it's strangely confusing, although completely obvious, right? Completely obvious. Not completely obvious?
Yeah.
Completely. Right? Yes. Right? Right? So this thing ends up looking like this, right?
Oh, that's an absolute
Right? This is how the absolute value is. Right? Because on the left side, all the lines, you have the x coordinate and then negative the x coordinate. On the right, you have the x coordinate and the same, and the y coordinate is the same. Okay. Right. Let's see. The x function f of x equals, say, 1 over x. No, let's do x squared. F of x is x squared. Right. And this you sort of know what it looks like. What is it? It's a parabola, right? Parabola, right? And you see that if you take right, the graph is going to look like points that look like x squared, right? The y value is always going to be the square of the x value. Right? Y value is x squared, right? And so at 1, you get 1, 2, you get 4, 3, you get 9, etc., right? And you see that this graph has some symmetry to it, right? If you put in negative x for x, if you put in negative x, you get the same one, right? Notice that it is symmetric about the x-axis, since if you replace x by x squared, you still get x squared. Right? So that is this equation doesn't change when you put in negative x. Right? So it's symmetric about the x-axis, and we only have to do half of it because we know the other half will be just a reflection. Is that clear? Is that clear? So just to tie it back to the symmetry, right? Right. What about this one? What symmetry did this one have? I guess you can just look at it. Different? Symmetric about the x for the same reason. If you replace x by negative x, you still get the same value. Right? The equation doesn't change. Okay, how about this one? F of x is 1 over x. So the domain is everything but 0. What does it look like? It's not a hyperbola. It's not, I mean, yeah, it's not what's called a hyperbola, but I guess it looks sort of like a hyperbola. Yeah. Right, but it is, as you sort of sketching, like it goes like this, right? At time 1, what's the value? 1. At time 2, what's the value? 1 half. At time 3, 1/3. Time 4, 1/4. Time 5, 1/5, etc. Right? At time 1/2, what's the value? 2. Right? At time 1/2, it's 2. Right? At time 2, it was 1/2. At time 1/2, it's 2. At time 1/3, 3. At time 1/4, you get 4. Right? Etc. Etc. It goes like this, and there's sort of there's this symmetry to it, right? And right, y equals 1 over x. What kind of symmetry does it have? Share? If I replace x by negative x, well, things change. If I replace y by negative y, again, things change. If I replace them both by their negatives, then I actually get the same equation, right? Because the negatives, I'll get negative y equals 1 over negative x, which is the same equation as y equals 1 over x, right? Okay. So it's symmetric about the origin. Right? And so it's going to we don't have to know half of it, because the other half will be gotten by reflecting.
So y equals 1 over x is just the reflection of fx equals 1.
No. The function. The function.
Oh, the
on
function
left
itself
side-
looks like that. Okay.
Yeah, the function on the left side is the reflection across the origin of the function on the right side. This one, f of x is the square root of 1 minus x squared. Right? In other words, y is the square root of 1 minus x squared for the graph. Okay, the last one. Okay, well, let's think. Let's think about the domain first. What kind of x's are possible?
It can't be a negative number. Well,
This can't be a negative number. Yeah, so this
Yeah,
has to
yeah, it has to be greater than
that's
0.
be, yeah. So what does that tell you, right? That,
Yeah.
right? So what does that tell you? We could write it like this, right? Because x squared and the absolute value of x squared are the same thing, right? So what does that tell you? What does it tell you about x?
So x would have to be it'd be very small. So it would be similar to the graph before, right? It would just keep getting smaller.
Well, okay, so first let's figure out the domain. So the domain here we see is that 1 minus x squared has to be greater than or equal to 0, right? And this tells us something about the absolute value, that the absolute value squared has to be smaller than 1, right? So that tells us that the x value lies between minus 1 and 1. Okay. So that is, this function doesn't make any sense outside. Okay. Does anyone recognize this? Anyone recognize this? Logan. It's a semicircle. Yeah. So if you think about it, this is actually the upper half of the circle. If you go from here, you can start from here and say, well, look, y squared is 1 minus x squared. If you square both sides, then you get y squared is 1 minus x squared. Right? And then you recognize that thing is a circle, right? But we've just taken the upper half of it here. Or you could plot points and eventually start to suspect that it is a circle. But this, by squaring it, you recognize it really is a circle, or half a circle.
Is there,
Yeah.
okay, this might be a silly question, but is there any difference between f of x equals square root 1 minus x squared and y equals the same thing? Is there any difference between?
So here's the function, right?
Yes.
Here's the function. F of x is blah. When I'm writing like this, I'm talking about the graph.
Oh, okay.
I'm talking about the graph. The graph is the graph, to spell it out, the graph of f is all xy such that y is equal to blah. That's when somebody writes, when somebody writes this sort of thing, that's what they're doing. Yeah. Let me make one sort of dumb observation. That is, if you look at the graph, then you can tell what the domain and range are. You can sort of read it off, right? So like here, I'd say, okay, what's the domain? If I'm looking at this thing, what kind of x's are legal? All of them. And then what's the range? All non-negative numbers, right? The range would be this, or to be more precise, the image is that. Here, right, and say, okay, what's the domain? All real numbers except 0, right? Because you see that it's got, for all x's except for 0, it's got an output, right? And then you look at what's the image? What's the image? The same. The same thing, right? Because you look at it and you say, well, look, I can get all y dot, I can get all, I get all positive values, I get all negative values, but I don't get 0. Right? There's no place where I'm on where I intersect the x-axis. Right? Here, right? Here you'd say, well, okay, so the domain is the closed interval from -1 to 1, and then the range is 0 to 1. 0 to 1. So not a deep observation. Okay, so let me put up another sort of strange thing. Suppose the graph of f looked like this. Like this. So there are a bunch of points on it saying, let's say that this is 3, this is 3, 1, 3, 2, 3, 3, 3, 5, and 3, 7. Okay. So here's the graph. Here's the graph of that. What does that tell you about? What does that tell you about? Huh? Becca?
It's not a function.
It's not a function? Why not?
Because for a function, the definition of a function is that for every input, there's exactly one output, and for the input of 3, there's multiple.
Right. So this is not a function, right? It says that f of 3, right? F of 3 is, well, it could be 1 or 2 or 3 or 5 or 7, right? It could be any one of those things, right? And so this is not a function. Right? If this were a function, it would be a function that takes on multiple values at a point, at the same input, right? Which is illegal for now. So later on, if you go on in mathematics and you go on to the world of complex variables, then it will be legal to have functions which take on multiple values at the same point. Okay. It will be legal, and you already start to see a hint of this with the square root function. Right? The square root function seems like it takes on 2 values. The square root of 1, well, it could be 1, it could be negative 1. Right? What we're hiding from you is that one can actually think of the square root function as a function, a so-called multiple value function. Just to entertain you, let me tell you actually how this works. What one does is you take 2 copies of the complex plane. To properly define the square root function, you take 2 copies of the complex plane and you cut them. Okay, you make a cut in them, and then you glue them together in such a way that when you cross over to here, you come up to the second plane. Okay, and then when you cross backwards, you end up on the first plane. Okay, and on the first plane, you have the positive guys, the positive square roots. On the second plane, you have the negative square roots. Okay, so it's on like a double. You take a double copy of your number system, basically, and once you cross over, you switch over to the other value. Okay, just for amusement, just for your knowledge, this is actually the origin of Alice Through the Looking Glass. Dodgson, right, was a mathematician, or at least a math teacher, and so he knew about this thing, which is called a Riemann surface. And so he thought, okay, I'll make up a story for this young girl about what happens when you cross through the looking glass into the world where everything is backwards, right? And this line here, this cut that's made, the Riemann cut, is the looking glass, right, or the forerunner of the matrix. Cross through the mirror into the matrix.
We should read stories in this class.
Oh yeah.
That would be fun.
Okay, so let's do a couple more. So there's this thing called the vertical line test that says that it says exactly what we just. It says something very obvious that if you draw a vertical line and it intersects the graph at more than one point, then it's not a function. Then it's not the graph of the function. So if any vertical line intersects the graph in more than one point, then it's not the graph of the function. Okay. But that's obvious, right? As long as if you know what a function is, you understand. You don't need to. It's sort of silly to even give this a name. It's not even worth giving a name, to be honest. Okay. Let me throw in one definition: a piecewise-defined function. Okay. So piecewise-defined function is something like this. It's a function. So let me just give you an example. It's a function where it's defined one way in one place and another way in another place. Okay. And we've already seen an example of this, right? It's the absolute value function, right? Is x is greater than 0 is negative x if x is less than 0, right? This is actually a piecewise-defined function, right? It's a function defined in pieces. Okay. So like this guy, as you see, right, between -1 and 1, it's the upper half of a circle, right? But from 1 onwards, whoops, I should be careful. So, and here it's open. But from one onwards, it looks like the 1/x function. So it goes like this. Pretty simple idea. But we'll need it. Let me sort of close up with a bunch of questions which will test if you understand the notion of a graph. So basically, if you can do these problems right now, then you understand what we're doing. So here is the line y equals x. Here's the line y equals square root of x. Okay, and here is the point 6. Okay, let's call this point P. Let's go up vertically to P. Let's go sideways and call this point Q. And we go down again perpendicularly and call this point R. What are the coordinates of P, Q, and R. So if you understand what a graph is, then, well, this will check if you understand what a graph is. And then we put another one, in case you finish the first one. What are the coordinates? What are the coordinates of those points? This line is the graph of root 2 over 1 plus x squared. This is the graph of the function x squared. From minus 2, we go up. We go sideways. Here's P, Q. We go up again, again, find the coordinates of P, Q, and R. Okay, let's start off. Yeah, Alex, okay, go ahead.
Okay.
So what's the coordinate of P first?
The coordinate of P is 6Q.
6 what?
Uh,
6.
okay, I want to do this now.
What did you say?
6Q. Because you know that.
6Q.
Can
Q
you
is
just,
this point, right?
yeah, but can't you just say that it's like, because you know that that's how far?
Q is the name of the point. Right? Point with like two coordinates on it.
I gave it a try.
Okay. Stop it. So if this point is 6, what's this? You know what the
P is 6, and then I don't know what is root 6.
root 6, very good. Right? Root 6. Right? Because if you're on this line, it means that your y value is the square root of your x value. Right? Okay. What about q? Well, you know the y value, right?
Yeah, so root 6.
Y value is root 6, and you know that q lies on the line y equals x.
Oh, it's root 6.
Root 6 is 6. Lower.
I have a question.
Yes.
So for like that first one, where P we know is 6,
Mhm.
so X is 6,
Mhm.
but then, so wouldn't it be like, Y would be 36?
Y is the square root of x, right? So the y value has to be the square root of the x value.
Okay.
Okay, right. So this would be root 6, right? And then let's drop that down, right? So here we already know the x value of r, right? What's the x value? Root 6. Right? And we're on the line y is the square root of x. So what's the y value? Square root of the square root of 6. And then we do something similar here. maybe we want to